You open Google Authenticator on a brand new phone. Airplane mode is on, Wi-Fi is off. There is no signal at all. You tap the account, a 6-digit code appears, and somehow Google's server, thousands of miles away, knows it is correct. So how do your phone and Google's server agree on the same 6-digit number every 30 seconds without ever talking to each other? By the end of this video, you will see exactly how this trick works and the one tiny secret that makes it all possible. Here's the obvious way. Your phone asks Google's server, "Give me the code right now." The server makes one up and sends it back. Simple, right? But that breaks immediately. If your phone has no internet, no code. If Google has 1 billion users hammering this every 30 seconds, the server melts. And worst of all, anyone who sniffs the network sees the code in transit and replays it. So the goal is the opposite. The phone and the server must somehow produce the same number at the same moment without ever sending it. That sounds impossible. But there is a clean way to do it, and it has been an open standard since 2011. It all starts with that QR code you scan when you first add an account. That QR is not your password, and it is not a one-time code. It is a secret, a random string of bytes, usually 160 bits long, encoded in base 32 so it survives a camera scan. The server generated it, saved its copy, and showed you the QR. Your phone scans it, decodes it, and stores its own copy. From this single moment on, both sides hold the same key, and the secret never leaves either device again. No login request will ever carry it. This is the only time it crosses the air. And that is why protecting that QR screenshot matters so much. The second ingredient is time. Every computer on Earth agrees on Unix time, the number of seconds since January 1st, 1970. Both your phone and Google server take that number, divide it by 30, and round down. That gives you a counter that ticks up by 1 every 30 seconds. Right now, at this very moment, your phone and Google server share the exact same counter value, even though they have never spoken. That synced counter is what replaces talking to the server. It is a clock both sides can read, and they both read the exact same tick. Before TOTP, there was HOTP, RFC 4226, published in 2005. HOTP uses a counter that increments every time you press a button. The problem? The phone counter and the server counter can drift apart if you press the button without logging in. TOTP, defined in RFC 6238 in 2011, swapped the manual counter for a time counter. Now both sides count automatically. No button presses needed, no drift from missed presses. Same math, smarter input. Now we have two ingredients ready. The secret you both stored when you scanned the QR, and the time counter that ticks every 30 seconds. We feed them into a function called hmac sha1. Think of hmac as a sealed mixing box. You drop the secret and the counter in one end, and out the other end comes a 20-byte hash, a chunk of bytes that looks completely random to anyone watching. Same secret plus same counter every single time gives the exact same 20 bytes. Change either input by a single bit, and the entire 20 bytes scrambles into something unrecognizable. That is the magic ingredient. The match is built in. And critically, hmac is a one-way street. Knowing the output 20 bytes does not let an attacker reverse engineer the secret. So even if someone sees your 6-digit code, they learn nothing useful about the key. But a screen cannot show 20 bytes. It shows 6 digits. So RFC 4226 spells out exactly how to shrink that hash down. Step 1. look at the very last byte of the hash and take its bottom 4 bits. That number, between 0 and 15, is your offset. Step 2. Jump to that offset in the hash and read the next 4 bytes. Step 3. Mask off the top bit, just so the number stays positive. Step 4. Take what is left, modulo 1 million. That always gives you a number between 0 and 999,999. Pad it with leading zeros if needed, and you have your 6-digit code. Both sides run this exact procedure, so both sides land on the exact same digits. Here is the moment the whole design pays off. You type your 6 digits into the login box. Google server takes its copy of your secret, the one it stored when you first scanned the QR, takes the current time counter on its end, runs hmac SHA-1, runs the exact same truncation, and produces a 6-digit code of its own. Then it just checks one thing. Do these 2 numbers match? If yes, you are in. If not, you are rejected. No code was ever sent over the wire from your phone. No call to a verify service. No round trip back to a database of pending codes. Just 2 machines on opposite sides of the planet doing the exact same math and arriving at the exact same answer. That is what makes Authenticator work in airplane mode. It never needed the network in the first place. There is one wrinkle. What if your phone's clock is a few seconds ahead or a few seconds behind? You would land in a different time window than the server, and your code would never match. So the standard quietly adds forgiveness. Most servers check 3 time windows: the current one, the one just before, and the one just after. That is plus or minus 30 seconds of slack. As long as your phone clock is within that window, you sail through. But if your phone is minutes off, login fails. That is why almost every Authenticator help page starts with, check that automatic time is on. Pause here for 1 second. What does this actually defend against, and what doesn't it? TOTP kills 2 big classes of attack. First, if someone steals only your password from a leaked database, they still cannot log in, because they cannot guess the next 30-second code. Second, if they sniff one code off the wire, that code is dead in 30 seconds anyway, so replay is useless. But TOTP cannot save you from a fake login page that relays your code to the real Google in real time. The attacker just forwards your 6 digits within the window. And it cannot save you if the secret itself leaks, from a server breach, a careless phone backup, or a screenshot of the QR code sitting in your photo roll. Quick question I want you to drop in the comments. How do you back up your 2FA secrets? Cloud sync, paper code, a hardware key, or you just don't? I read the answers. Here's the payoff line, the one tiny secret I promised at the start. Google Authenticator is not magic, and it is not online. It is just 2 calculators, set to the same starting number, both winding forward in lockstep with the clock. The code is not a code at all. It is just where the clock hands of 2 synced calculators happen to land in this 30-second window. The server is not telling your phone anything. They are dancing to the same beat in silence. 3 things to take with you. 1. There is a shared secret stored on both sides at the moment you scan the QR. 2. Both sides agree on a time counter from Unix time divided by 30. 3. hmac SHA-1 plus dynamic truncation turns those 2 numbers into the same 6 digits on both sides. If you remember one thing, remember this. The code was never sent to your phone. It was computed on your phone. That is the whole trick. 2 machines, 1 shared secret, 1 shared clock, 0 conversation. If you want to go deeper, RFC 6238 is short and surprisingly readable. So a question for you to chew on. Now that you know the secret is the whole castle, where on earth is yours actually stored, and who else can read it? If this breakdown helped, hit like, subscribe so the next one finds you, and share it with a friend who still thinks the code comes from Google. See you in the next one.